we continue to think about this same example, we could repeat this entire idea with 16 rectangles and then use 32 and then 64. And each time we would be shrinking the width of each rectangle in order to fit the rectangles in this overall width from 0 to 4. So what we're really doing though is we're taking the width of a rectangle and multiplying it by the height of the rectangle and adding that idea up. Right? There's just a bunch of rectangles whose area we're finding, and then we're adding them up. And we know that the shorthand for something like this would be a summation. We're adding up a bunch of area formulas. And so since we're just adding up a bunch of area formulas, we're really just thinking about that idea. And we're adding up from 1 to n, where this really talks about the number of rectangles we're using. Right? So we initially found the sum using 4 rectangles. We went from 1 to 4. And then the second time we did this, we went from 1 to 8, because we had 8 rectangles. And notice in each case, the height of our rectangle was x squared plus 1. It's always found by the same expression. And it was the width of our rectangle that was changing, or the value of x was changing. And hopefully it's obvious that as the number of rectangles increases, and really as it goes to infinity, the sum of the area of the rectangle will be better than anything we could possibly have. And if the area of the rectangles, or if the number of rectangles is infinite, then the width of the rectangles would have to be infinitely small. And so the limit as the number of rectangles goes to infinity of the sum of all of their areas would just be the height of them times the width of them. And change in x, right? Initially it was 1 unit, and then we had widths of 1/2, and then we go 1/4 and 1/8, just to continue a pattern. Eventually it's going to get infinitely small, but this is really just an expression for height times width. And when this occurs, what we're really doing is now we're integrating. We can think of it like this symbol is morphing into this integral symbol. And we'll be integrating, in this case, over the entire width from 0 to 4. And we're breaking that entire width up into infinitely small parts of heights at x squared plus 1. And notice that when we integrate, this would become 1/3 x cubed plus x 0 to 4, which would be 64 that 56 thirds, or about 5 feet. That this is the exact value for the area under the curve, and it would be the exact distance that some object had traveled. But this is really the key idea right now, is that we're using this idea of area, adding them up, that if the number of rectangles goes to infinity, it would be very accurate, exactly accurate. The width of those rectangles will be infinitely small, and this is how it's related to an integral. In an intuitive way, not a hard proof-based way.